Good morning, everyone, or good afternoon, as the case may be. My name is Aaron Johnson. I am the Executive Director of the American Institute of Professional Geologists. It's my pleasure to welcome you today to our AIPG Lunch and Earn series. Before we get started, just a couple of quick notes. If you need continuing education credit for this webinar, the certificate for the webinar will come to the same email address that you used to register for the webinar. Secondly, if you're in New York State and you need this credit for your New York State registration, you will have to complete a 5-question assessment. This is a requirement from the New York State Education Department. You need to answer 4 of those 5 questions correctly. You can take that assessment as many times as you like, and we will put the link to that assessment in the chat toward the end of the presentation. So keep your eyes open for that if you need this for your continuing education for New York State. Well, it is my pleasure today to welcome Darren Beckstrand as our presenter. Darren is a senior associate geologist with Landslide Technology, got a bachelor's degree and a master's degree from Portland State, and has more than 2 decades of engineering geology experience. He is a certified engineering geologist as well as a registered professional geologist, and he's worked both in the mountainous areas out west, Montana, Idaho, Alaska, and has some experience in the mid-continent where we throw sinkholes into the mix. Darren, I really appreciate you taking some time to share your knowledge and expertise with us today. The floor is yours.
Yeah, thank you. Thanks everyone. I appreciate the opportunity to present here to AIPG today. As Aaron mentioned, I've been from Portland State, and I've been working since I graduated in 2020 for Landslide Technology for my entire career. Haven't moved around very much. I've been pretty fortunate with that. And in that time, since I've been working here, I've been working with large data sets in the realm of rockfall hazard rating systems, and which then evolved to geotechnical asset management. And I'm working with those data sets starting in Montana, and then did a little bit of work in Virginia, expanded the realm of geotechnical or rockfall hazard rating systems in 2010 for the state of Alaska, helped develop an unstable slope program and the geotechnical asset management program for Alaska. And since then has been working in Missouri, Tennessee, Idaho, Illinois, and really helping in many of these state DOTs with developing their asset management program to include these geotechnical assets. I'm also a co-chair for the Transportation Research Board's subcommittee on geotechnical asset management. And again, I thank everyone here today. There we go. And so what are the geohazards that are affecting the transportation system? These are a lot of examples from Alaska. Debris flows, erosional slopes, rockfall coming down into the highway, affecting the transportation network. These are obviously not planned occurrences, major rock slides that can close a road for a long time, or these shallow slope failures with the trees, and including normal landslides and translational slides like this. Over time, all these types of maintenance events can occur and add up to quite a bit of disturbance and blockages and lack of the transportation infrastructure, especially in Alaska, where there's not a detour. Often there, a detour might include driving 8 hours to a ferry terminal, getting on a ferry for 8 to 12 hours, and then continuing further south after you drive through a mountain that's shared through with a railroad tunnel. The transportation networks there especially need to be reliable and resilient, and as few of geotechnical hazards as possible that inhibit passage of traffic. This is an example of a hotspot map south of Anchorage on the Seward Highway, where there's been a lot of work done in the past few years with rockfall hazard reduction through a mitigation program, and extending this type of maintenance tracking database to the entire state. You can see how you have a lot of different adverse geotechnical events over several years. And as you plot these up and develop a heat map of where all these things are occurring, the concentration of where you might need to focus your energy and time and investment can make themselves evident. But clearly, this type of a sizable problem spread throughout the state where you have about 7,500 adverse geotechnical events occurring statewide, you need to have, or it would be not, it would be ideal to have a nice systematic system of addressing, recognizing, and evaluating these things and comparing them one another. And that's a very good reason to manage geotechnical hazards. So typically, the normal approach, hopefully it's becoming less normal, but a typical approach is to let the ground tell you where you need to fix the slope. So the ground falls, a rock falls into your highway, you have a landslide, and you have to respond. But there is a better way. That's also the most expensive way to typically do it. But large owners like the DOTs that were in the examples there will have hundreds of vulnerabilities, producing thousands of adverse events across the entire highway network. A systematic and rational approach to help prioritize risk reduction in a cost-effective way is needed. The transportation industry uses an approach called transportation asset management. And that's something that a lot of us know about on the periphery through the National Bridge Inventory. And notice in all those slides I had up there wasn't a single broken bridge. That's because they are more actively managed, and they've been recognized as a manageable asset, and they actively manage those. The federal government requires states to manage their bridge and pavement inventories as part of an asset management plan. And the same principles can be applied to geotechnical assets to help identify, assess, and reduce those risks and reduce expenditures for a similar network outcome. So what is transportation asset management? It's a strategic and systematic process of operating, maintaining, upgrading, and expanding physical assets effectively through their life cycle. That's from the AASHTO. Transportation asset management for bridges and pavements is required, and it's encouraged, which is an improvement from the past, but it's encouraged for ancillary assets. Ancillary assets are things like intelligent transportation system, the signboards that tell you how long the traffic delays are, guardrails, sound walls, signage, striping. Those are all, and including geotechnical assets like retaining walls. Those types of things are encouraged to have an active, proactive management program for the ancillary assets. But what does it actually mean when it comes to the folks in the states to manage the program? It means that no federal directive is required, so it may mean that it's likely considered optional by management. Fortunately, there's enough states that are starting to recognize that there's a benefit to it, so that's changing a little bit. The application of TAM business models, the geotechnical assets, it's kind of a difficult thing to explain. So I've tried to do it here in an explanatory paragraph that highlights a couple different things. So imagine you are a geotechnical professional working for a DOT, and you want to be able to state these things. So my department has 5,000 geotechnical assets. So that, again, programs provides you the inventory to know what you own. And those 5,000 geotechnical assets, 75% of those meet performance criteria. So you set expectations, and then you measure the performance of your assets to those expectations. Pavement does that quite often. They'll have dashboards up and ready saying, 90% of our interstate pavements are in good condition. That's something that we can also do for geotechnical assets. We also are able to estimate deterioration. If we do nothing in 10 years, instead of 70%, it'll drop down to 65% meeting those performance criteria. And that uncontrolled deterioration will have this cost that we can estimate. that deterioration will result in $10 million of direct costs and indirect costs of $30 million. We're forecast to have 8 road closures per year, growing to 9. So that's, if you don't do anything, you can estimate the increased cost to the department and the taxpayers, and the number of adverse events and road closures due to failures of those geotechnical assets. These are all hypotheticals, by the way, but it helps illustrate the point I'm trying to make. And also critically, it can help you set budgets to achieve the goals that you have. So in this case, if we invest $2.5 million per budget cycle, reduce unforeseen state expenditures by 50%, reduce forecast road closures to 7%, and project that 75% of those assets meet performance criteria. So it gives you the ability to set budgets and then plan where to spend the money in several different ways. And this is something that the pavement and bridge management programs do for the states to make sure that they don't have a bridge failure, close the highway for weeks or months at a time. Of course, those still happen, but the goal is to see those reduce. And same thing with pavements. A chip seal that preserves pavement performance is a lot more affordable than a full replacement of the entire pavement profile. So examples of some geotechnical assets, starting at the top, we have a nice highway down here. We have erosion control and retaining walls being shown at the top, the geologic hazards and processes of material coming off the slopes above and affecting the performance of the roads. Mitigation measures that help ensure the performance of those rock cuts in this case, and same with the drains, reducing pore pressures. The rockfall ditch there is critical to the performance of the rock cut, to make sure you have a capacity to contain rocks on the road, contain rocks in the ditch so they don't get on the road. Subgrade repairs, geotextiles to help reinforce the subgrades if it's marginally stable. Geotechnical instrumentation, embankments that are susceptible to slope movements, and the other soil anchors, erosion control, and retaining walls that may also be there helping ensure the performance of the highway. And of course, scour protection at the base of the road to make sure that the rivers don't do too much damage and really start to take things away. The current state of geotechnical asset management in the U.S. Back in 2010, we did an informal survey of several state DOTs. Those are highlighted in black, and those are the ones that had a rockfall hazard rating system in place. Since then, additional states have been focusing and expanding their asset management system. So some states that don't have a lot of rock slopes, since this is most of the states of course, on the West Coast had a lot of rock slopes, or the Western U.S. had a lot of rock slopes. So they were some of the first, and then in the Northeast, they had some of the first programs that evaluated that stuff. But some of the Midwest states and Southern states have been focusing on their geotechnical assets, such as retaining walls, and expanding and addressing those things since 2010, and especially more in the past 5 or 6 years or so. It's starting to gain some steam, and states are doing it. So a few key components, kind of highlighting again that explanatory text in the previous slides. Key components of a mature GAM program. I kind of call out mature with some intent. You don't have, if a state DOT doesn't want to go in both feet first into the pool, they can dip their toes in and start with an inventory. There's no required way to accomplish these things, and there's no wrong way to get started. But what is critical is that you understand that a lot of these things are great to have if you own, thousands of miles of highways. So key components of that mature GAM program, it provides an inventory. A lot of owners don't know what they have, don't know what's out there, don't know where walls are. And just because you don't know doesn't mean you don't have any liability and that there's no cost involved, because those deteriorating assets will make themselves known usually in the most inconvenient time. It also provides a condition assessment. What kind of shape is it in? Is it in a good condition that is expected to preserve performance for a long time, or is it in poor condition that needs major repairs? Risk estimation and evaluation. How many traffic interruptions may occur from these geovents from these unknown assets that we might have out there? And then financial planning, how much budget should we set aside for these things over time? So jumping into an inventory, those are often started with a desk study of where assets may be, calling out this topographic or hillshade map of Montana. You're going to focus in on the western part of the state. That's fairly obvious. How this was carried out the first time in 2003, as we sat in the basement of Montana's headquarters and just went through their road viewer, a group of us, for a week, and jotted down the coordinates of each one of the slopes and said, okay, we don't have to drive 2/3 of the state, but we do have to go to these areas in the rest of the state. And we also gave them preliminary assessments of A, B, or C, if that's possible, to help focus where the more field time would be required. Condition assessment. Most states use a modification of the Rockville Hazard Rating System. This is the cover of that National Highway Institute course that was developed in the mid-90s. And this is where a lot of the states really started to get a handle on where their rock slopes were and what type of ratings they would get, not necessarily condition. What the RHRS would do is give a score output. The higher the score, the worse it is. It's meant to help really identify where some of your worst, where your worst, 3 dozen rock slopes are out of, an inventory of 1,000, to help with that worst first type of approach. Unstable slopes also use a similar approach. Those have been developed for the USMP, or the Unstable Slope Management Program, that was developed about 10 years ago for the federal highways, and for FLMAs, the federal land management agencies like the Forest Service, National Park Service, and whatnot. Later, geotechnical asset management studies built upon these frameworks for condition and risk. So the condition of good, fair, poor, and the likelihood of adverse events occurring from rocks coming off of those unstable slopes, or the landslides dropping away. A site inventory and site assessments are typically the best place to start. As I said, the site ratings, you collect a lot of different information. So I'm going to go through the Unstable Slope Management Program, kind of touch on some highlights from the USMP form for the federal land management agencies. That program is contained largely on a 2-sided piece of paper, and you start with the location information, highway mile points, left or right, lat long of where it begins and ends, some geometric data of the site, and it has geologic data and judgments incorporated into the ratings. Some performance data, rockfall history, how often maintenance has to act on there, and consequences of the failure, how much traffic relies on that road. If you don't have good traffic numbers, does that road go to a very important boat dock for the Bureau of Land Management? And if that road was closed, then the local economy starts to die down. Those types of judgments and assessments can be built in there. If you're in the national parks, is there national or environmental or cultural impacts if this unstable slope continues to fail uncontrolled? So those types of evaluation forms are set up specifically for special purposes, for national parks in this case, or in those specific cultural and environmental impacts. Zooming in a little bit on the 2 pages forms, you have site information, a preliminary rating category, slope hazard ratings, and a risk rating. So you have, over 24 different things to evaluate on each one of the unstable slope sites that you might have throughout your state. So I'm just going to touch on a few things on this as I go through the presentation. The site information portion of it, this is the top quarter of the page 1. You have things like what management area and what date the slope was evaluated, hazard type, rockfall, landslide, the road number, and other site measurements like site distance, and I'll go over that, length of the roadway affected, slope height, et cetera, speed limit, block size, and some comments. And it's always good to have some comments in there to kind of give a quick synopsis of what the evaluator wants to most effectively communicate about the site. This is a lot of information. A lot of the information can be pre-populated through that desk study. And the intent for all this, believe it or not, we try and spend only about 15 minutes to 25, 30 minutes at a complex site, going through and evaluating the entire site and then going on to the next one. So all this information does facilitate or does allow a pretty quick assessment of the sites. Some example information being gleaned. So you have the road and trail number. Trail number, that's something that the National Park Service specifically wanted in this one. They wanted to be able to evaluate the importance of high traffic or even low traffic trails and how they're exposed to geologic hazards. So that's pretty unique in the USMP system. But corridors, highway numbers, route name, classification. If you're not familiar with, of course, we're all familiar with the interstate system, but most DOTs have primary arterials and secondary routes and whatnot, and those can often be those are important to gather and understand, so you can help gauge the importance of that route and the performance of the roadways that go next to it. You can also evaluate if it's a sole access route. So especially some of these western states, they'll have a highway number that just goes to a dead end. And if that slope fails and no one's able to get in or out, and that's a different importance than something with an easy detour. Hazard information that might be going on there, rockfall, discontinuity controlled failures. So things like planar, wedge, or topple failures are more of the hard rock type of failures. And then also differential erosion, failures that are caused by differential erosion. So in the southeast, more sandstone, limestone interbeds, where you have the more weatherable prone materials weathering out and destabilizing the sandstone above. Back to some pictures instead of just text, some nice examples of planar failures. This is a slope in Montana where you can clearly see the discontinuities failing out here. This is near West Glacier on Highway 2. If you've been to the area, large wedge failures can clearly produce rockfall for either all at once or for a long time as things ravel out slowly over the decades since construction. This slope was constructed just like this, and over 20 years or so, this wedge failure formed. Topple failures. I'm standing in an opening tension crack high above a rock slope in Montana, where in this case, we wanted to make sure that it was still moving before the state monitor or decided to do anything with it. And yes, it was moving, and the tape-x densometers and crack meters did demonstrate that. Oftentimes you'll have a slope where the structural condition of the slope is not as clear. This is more normal. A bunch of intersecting discontinuous joints combining to have the 1 to 3 foot blocks fail out. Differential erosion failures of the siltstone sandstone beds, in this case in Montana, where you might have large blocks failing out over time. A recent picture from Tennessee of differential erosion slopes that were being evaluated for Tennessee DOT. Talus raveling out over time. This isn't typically considered a rock slope, but if the hazard produced is rockfall related, rocks rolling from the slope onto the road, it's rational to evaluate this as a rockfall hazard. Landslides is something in the USMP that was evaluated. Where is the slide located relative to the road? We have some of that basic information. Is it above the road, below the road, or worst case, it's both. It's going through the road, taking the road down for a ride. Type of slide, best judgment is what's warranted here. Almost every slide is not a textbook example of a nice rotational failure or a translational failure. But here's some photos kind of showing those characteristics of rotational failure, where you have the material here kind of rotating backwards into the headscarp. Again, sliding down and rotating slightly near the headscarp of the slide. And at the toe of a slide, you'll often see you can sometimes see the slide plane and the weak slide material on top. This one is at a beach. And so you would, the slide mass would be getting eaten away by wave action and producing the fairly uncommonly seen slide plane right at the base of it. And then translational failures, this slide was just popping up and just raising the road up. There's no big rotation of the slide mass here. And like I said, a lot of these are not textbook examples. All these 4 slides are the same landslide on the coast of Oregon. And so you have characteristics of all these types of movements in the slide, and in a single large, especially large slides. This was a pretty large slide that had been moving for over hundreds of years. Other translational failures. This was a project in the Oregon coast where we had the pre-splits coming down the rock face, and we were paused having lunch, and we noticed that the pre-splits were offset. That's not normal. That's not good. And so here I am, improvising a straight edge tool of a bunch of survey stakes and some electrical tape, showing that this thing had the upper part of this slide had slid, several inches, since this slide was only, or this cut was only a year or so old, so it was happening pretty quick. Earth and debris flows are in the USMP system are categorized as landslides. One from Colorado. I know several folks here from Colorado. This is a Salt Creek slide. I think I got the name right. Then the headscarp from another debris flow on the right. Erosional failures can be classified in these also as landslides. Getting these in the inventory and condition assessment so you can prevent them rather than just allow them to eat away the road is important. And same thing with easily erodible material slowly eroding out on oversteepened slopes that your highway's sitting on. And often here in the Pacific Northwest, these slump failures are the most common landslides that we see, where just the overburdened soil on the side of the road just slumps out during heavy rain. Other rating data that's collected in these types of programs are numerical data rather than judgments on the nature of the slides of rock slopes. We are looking at slope height measured as the vertical soil slope. We're estimating the axial length down the slide. If possible, you can do some reconnaissance to find the slide toe, but oftentimes it's pretty masked by embankment riprap or fill or something along those lines. You don't always have that clean toe coming out of there. So you have to use your professional geologic judgment to help define those, and your equipment that you use are typical handheld equipment of a laser rangefinder is wonderful. A clinometer and tape and doing some trigonometry, or better yet, having your Excel sheet do some trigonometry while you're out there is a good way to go about it. Another type of a measurement data that is collected in these is a sight distance. And that is something that as a traveler, you typically understand that if there's a sudden surprise in the road, you want to understand that that's a risk to you. And as I'm sure we've all done, coming around the corner, you see something and a deer or whatever, and you have to quickly stop or slow down to avoid the hazard. So this is an estimate for, say, a rock being in the road. And so the evaluators are typically on site doing our best to safely during live traffic to measure sight distance. So we're often not idealized like in this photo of walking down the travel lanes. We're often in the shoulder, or we'll use our rangefinder to estimate that sight distance. So again, 15, 20 minutes on site, you're doing things pretty quick. Yeah, and we use a roller tape or a laser rangefinder to do that. A couple examples, sight distance. If a rock came rolling off the hill here, you're going to see it while you're flying down the road at 55, and it's going to be, well, Montana, probably 70 miles an hour. But you're going to see it. You're going to be able to avoid it. But right around the corner, if you're coming this direction and this rock's in the road and you come around this corner, even though it has a 35-mile-an-hour speed limit on the corner, you still don't have a lot of sight distance, and the sight distance can be blocked by the guardrail, vegetation in the ditch, or other material in the ditch that is hindering sight distance. So that's an important risk aspect that we measure while we're going out there on site. Other type of data that is recorded is block size. You would expect big blocks like this or large volumes like this on the highways or on trails. That's going to rate very highly, right? Instead of, if this rock fall was just this rock down here, you would say, well, that's not great if it's flying down the hill and goes through a windshield. But the risk is greater for these larger blocks coming down. So a lot of it's intuitive with how these are rated. Jumping on down to the preliminary rating from the site information tab, there's several different categories on here. Oops. Noticing that you have I could go on that on a later slide. But yeah, several different categories for landslides, for rockfall, and how it's scored. Slope types are hazard criteria for landslides. They focus on impacts to the road and trail. Hazard criteria for rockfall focuses on size and frequency of the rockfall and the ability to keep the debris from the road or trail. And risk is something that you can compare on both slope types in the USMP system. What are the consequences of failure? How quote unquote important is the road trail? And in this case, you can do it based on traffic loads coming across the top here, or if you don't have traffic counts, some guidance for opinion. And note that this all has A, B, C, or D type of markers, designators on it, so you can help add up and define which categories add up to what in this case. So all these ratings are exponential. Notice that across the top, 3, 9, 27, or 81. And again, that's to help bring the high hazard slopes to the top, regardless of what brings them to the top. A minimum of 1, it does max out at 100. And so each individual category score here is based on this 3 to the power of X. Some categories are based on judgment and approximations, and others are based on calculations from the site information portion of the form. For example, this is a score that evaluates the the economic importance. So ADT divided by 50, square root of that, gives you the X over here. Similar to roadway length affected, length recorded in site information at the top of the page. The exponential formula is down here, a curve plot shown through here of how that changes throughout the out that category. And it's how much of the road is exposed to that hazard of either the rock slope or the landslide. Going through a quick example, if a slide is measured at 339 feet along the side of the road, what's the score? 339 divided by 25 gives you this, gives you the 3.68 of the exponent and a resultant score of 57 points. So this is why it's good to have a calculator or a database or a data entry platform help you out with these calculations rather than either pulling it off on a chart on site or doing the math on site. You're trying to rapidly go through it. And those are ones based on site measurements. Other ones are based on the opinion or the judgment of the experienced geoprofessional that's on the site to evaluate it. So to highlight that approach or those requirements, the ditch effectiveness. It's based on history, judgment, and site observations. Slope height and angle, ditch width, depth, and shape, the anticipated volume of debris that ditch would have to collect, and especially launch features. That is something that it takes a little bit more of a trained eye to help understand what the launch features are if you can imagine a rock falling down the slope. So some photo examples after this slide is we do have some text and some explanation that goes with it. So 3 points, the low score of it, good catchment. All or nearly all falling rocks are retained in the ditch, all the way to 81 points, no catchment. No ditch or ditch is totally ineffective. All or nearly all falling rocks reach the road. So if you have a highway, you'd want a ditch to look like this, nicely regraded. There's no pile of debris at the bottom to help redirect falling rock out of the ditch. Ditches can be improved to get this to better perform for the anticipated rock coming down here. Here's concrete blocks to absorb energy below the highway, concrete barrier for the clear zone safety requirements to make sure that this also does not become a roadside hazard. And for splatter and for falling rocks, you have a fence extension on top of the barriers. So that's a good performing ditch. That's good ditch effectiveness. Other clues that this ditch that is, it's a pretty big ditch. It's what used to be called a Ritchie ditch. You have some damage being shown up on here, some rocks coming down and even damaging the concrete barrier and impacting the roadway. So that's some signs and clues that evaluator used to say, hey, this ditch, it's big, it catches most of the stuff, but the rocks coming off that slope, it's too tall. And they will still fly out and break apart and only have a moderate ditch effectiveness. Again, this one has a bit of a launch feature right here coming off there and a relatively small ditch. And comparing this portion of the ditch to this portion, you usually want to take the more conservative approach and take the reasonably worst case scenario from a slope, not just look for the best parts of it. You're not trying to give brownie points to these slopes, trying to accurately assess the risk. This one it's pretty narrow ditch and pretty tall and irregular, so it's a pretty limited ditch effectiveness. You can probably imagine most rocks coming down that will be able to escape that ditch with relative ease. And this one, it's also limited. You're on a turn, which doesn't matter on ditch effectiveness. That's a different risk or category to be scored. But the big one on this one is this launch feature. As the rocks come down that slope, all of them are going to hit this bench. and it's inclined such that they all get redirected right out onto the road. So this one would really get docked in the score category for how that slope is redirecting rocks off the road. And this ditch is, it's not uncommon, especially in mountainous areas or highways, two-lane highways connected in or constructed in the 50s. The ditch might only be a couple feet wide. This is a forest road ditch, and this one is from a picture from earlier. So this is limited ditch effectiveness. And no ditch effectiveness, sometimes these the contractors back in the day, they said, well, the road can fit, so I'll just put it there. And the owner said, okay, save me some money. But this one doesn't have any ditch effectiveness. Rock comes off of here, it's going to go drop right in the road. And on Going to the Sun Road in Glacier National Park, there's also there is no ditch in that entire road. So if you've ever been there, it's a great place to visit. It's a great place to spend as little time as possible underneath the rock slopes also. So at the end of this, we have the preliminary rating. Add up all these things, evaluate them, and you get a preliminary rating. And you add them up, and if you have a fair or poor based on the sum range, you flip the sheet over, and you can continue doing a more detailed evaluation of the site. So turning that form over, we have the slope hazard rating through here, and several of the categories: slope drainage, annual rainfall, slope height or axial length that we talked about before. Landslides have categories such as thaw stability, maintenance frequency, and movement history, while rock slopes have some also rockfall related maintenance history. Then also the geologic character. This is where the ability for a geoprofessional and a geologist or a qualified geological engineer to come through and evaluate these types of more qualitative aspects of the slope is important. And so again, those are evaluated on a 3 to the power of X type of scoring system, 3, 9, 27, or 81. From rough irregular to undulating and planar to clay infilling, open or slick sided. So you can imagine the reduced friction that joint surface would offer up to resist sliding and failure. And it can roughly correspond to the joint roughness coefficient. If you're familiar with that, that is an approximate measure that helps evaluators guide their opinion to a joint roughness coefficient that's been in the literature for several decades. Some photos of some example photos of the rock friction score. So this is rough irregular. I think we can all agree that that makes sense. Undulating, it's especially common in basalt columns and stress relief joints. Planar failures. This photo is also from basalt, so it matters the orientation or how that friction is going to interact with the orientation of them, which are judged separately if they're continuous adverse or discontinuous favorable. The things like that is how you evaluate these. Some more examples from Alaska for these planar joint frictions. This is on the road to Valdez, and I was in awe when I drove through here, in 2010 or so, of how massive the structure was in this area. But this is a good example of continuous planar adversely oriented joints. And also forming those ones in a topple failure mechanism also. And clay filled in, slick and sided, that is a good sign that any sliding on there will be facilitated by the weak clay material and the pore pressures also. Breaking it down into the risk rating. So those examples were shown over here through that rock friction score. Again, we add up for landslides certain categories from the front of the sheet and from the back of the sheet for either landslides or rockfall, and then we jump onto the risk rating form. So we have a a qualitative number for the, or quantitative number for the hazard scores, and then you can jump into the risk categories. I'm just going to highlight one on here. It's the percent decision site distance. So that's an estimate of how quickly you are able to respond to that. I used those two photos as an example earlier on. Again, it's 3, 9, 27 points of how the measured site distance compares to the AASHTO recommended design value for that site. So this site, as an example, has a 520 or has a 175-foot long site distance measured around this tight corner. The recommended site distance for that speed limit is 35 miles an hour, so it's 525 feet. Do this complex equation. So, of course, every good presentation has complex equations. So here's mine. All these numbers plug into an exponent of 4.33. That scores up over that 100 points. So it caps out at 100 points. So instead of the 116, it gets capped to 100 points. So those are the site distance scores on the hazard, on the risk rating score. Total scores are then added up, and then you can use all these numbers to, there's the same number of categories in the USMP for landslides and rockfall. You can then say, hey, this 600 score landslide is not as bad as the 700 scored rockfall, so I'm going to maybe address the rockfall site first. So that helps provide a little bit of decision support to managing all these inventory of assets that you'd have. So that kind of concludes the quick explanation of how those are rated. I'll try and wrap it up here in the next 5 minutes. That's a lot of data to collect. So a digital data collection platform is key. We've been using Esri products and ArcGIS and Field Maps or Survey 123 in our recent work. And you write all that information onto a shared geodatabase, regardless if it's on the phone or what rater is going out there. You can have multiple raters go at it all the time without having to combine databases later on. We use, when possible, the client's Esri platform permissions, so they own the data all the time. So that's important for a lot of clients. They don't want to have to, if I screw up, we get fired. They still own the data that we collected for them. They don't have to have any ongoing service agreements for it. So it's always owner control. That's IT security is something that's gaining in importance over the past few years. Slope condition for rock slopes. We use these in a variety of different ways. Communication is one of the main ones. So you want to be able to explain to your manager how many of the rock slopes are in poor condition. So you don't get into the weeds and into the nuance of 25 is not as bad as 20 and so forth. So you want to say 5% of our slopes are in poor condition. Okay, understood. And so that kind of, as you get into more of the nuance in the condition range, that's where more geotech or technical folks can use that. For rock slopes, ditch effectiveness and the history of the site defines the rock slope condition. And there's a lot of words that go along with it, but in essence, low rockfall activity and high ability to stop the rocks is a good performing slope. And likewise, high activity and a low ability to stop the rocks, a lot of that, those rocks are getting on the road, and that's not a good thing. A mix of them will be up here in the middle of those fair categories. Maintenance cost estimates in Montana were queried through their maintenance management geodatabase and equated to proportionality of good, fair, poor conditions on the within those maintenance districts to come up with an estimate of how much direct costs are coming from state budgets versus cost sharing through the federal government. Slope deterioration, I mentioned those earlier on. It has the interesting title of where this was first described from the Rand Corporation, I think in the 60s, of analyzing the future. So very futuristic type of terminology goes with it. But what happens is we're asked questions. So this is how bridge inventory condition or databases got started, how pavement inventory databases got started before they collected data for 20 years to really analyze deterioration. But the experts in the field are asked the question in italics. Imagine there are 100 assets in the indicated condition state. So condition state 1, 2, 3, 4, 5. And after how many years will 50 of them have deteriorated to the next condition state or worse if no maintenance or corrective action had taken place? So we all get in the room, we think about it, we say, oh, 20 years, 19 years, 22 years, and so forth. And so that expert elicitation is turned into a probability, and all the costs that can go along with that get factored into the analyses that help set those budgets that I mentioned earlier on. We also can do mitigation cost modeling based on the condition state, looking at data from, you can see a little bit of a scatter in data for mitigation costs per square foot of rock slope versus condition state. But as condition gets worse, at the bottom of the plot here, it gets more expensive to fix, which kind of matches expectations, except for this worst one. I think there's a lower population here that skewed that number downwards. But this type of information really helps us understand large-scale implications of deterioration, implications being the cost of uncontrolled deterioration. But that one thing to recognize is it does not replace corridor or site-specific cost estimates. You can't just go through there, do an RHRS, and then say, this slope is going to take, $1.5 million to fix. You do have to go through there with a site-specific investigation and ability to define what's needed to achieve the goals of the site. We also looked at risk monetization using AASHTO principles of detour and traffic loads, and the probability of an adverse event based on maintenance history, of using various degrees of accuracy and precision in the data or in the reporting from maintenance personnel, all the way from it happened on this day, the closure duration was 39 hours and it slowed down for 3 days versus, it was around February or spring of 2013, and it took months for us to recover. So we had to be comfortable with some uncertainty and some generalization through those types of anecdotal reports. Looking at those risk results, we were able to develop a probability of event likelihood per square feet of rock face in each slope condition. And what that's based on is condition and size. And so, as you would expect, a very large slope, but in better condition, does pose a risk, but a smaller slope in a poor condition may pose more risk, even though it's much smaller. In this example down here, one slope might be 1,000 feet long by 150 feet tall, but it's a fairly good condition. You have a 0.5% of annual probability of an adverse event occurring, but one that's, a fifth of the length and, a third of the height, but in poorer condition has double the likelihood of a adverse event, but it's 13 times smaller in size. One other thing that we've incorporated on these is some risk tolerance based on the type of network system you're on. Your interstate, you're less tolerant of risk, but on those minor collectors, you may be more tolerant of risk. And those are something that we propose for the Montana system. A life cycle cost analysis is something that you can do from here also, of preservation activities, rather than allowing everything to deteriorate uncontrolled and spending a big dollar amount to reconstruct the site. You can push that back, for decades if you are maintaining and preserving the site performance versus reconstructing it when you have to. So that's where you see a lot of the cost benefit of preservation activities. It also helps you set those annual budgets for funding across the top and where the condition index will be over 10 years if for various investment levels. So if you are aiming to preserve network condition, and the network condition's 63, you need to, in this case, invest about $28 million annually to preserve that rather than allow it to deteriorate uncontrolled. So couple last slides right here. Cost to build again, this is for Montana. This helps illustrate some of the impact that going through the financial analysis is something that not all geos may be used to. But was a cost to build all those rock slopes again today, which might be an underestimate, but basically $4 billion. In Alaska, the geo asset value was greater than the bridge inventory value. So that's something that is kind of enlightening to many folks in the transportation industry. Preserving network conditions, reconstructing only, starting with the worst first, you'll need to invest about $35 million annually to preserve network conditions. But with those preservation activities built in, to achieve the same network outcome, you could invest $28 million. So over 10 years, about $70 million in savings from the same network outcome. Return on investment for those preservation activities, 114%. So that's what managers like to see. They want to see value in why they're throwing money at rock slopes and landslides rather than just reacting to them. Key takeaway for this is the performance of geological and geotechnical features are critical to infrastructure functionality, but are often discounted or not necessarily recognized by other folks in the transportation realm or in other large infrastructure owners. System-wide vulnerabilities of geohazards, even geonuisances, like those small shallow sloughs, often fly under the radar because they're not counted, they're not known. So if they don't know, then they're not considered. Treating them, there are these geo vulnerabilities in the same way as other engineered assets, such as bridges and pavements, despite their unpredictable nature, will help reduce risk and save dollars. And for us, the geo professionals, I think a couple of the three main things to remember is to be comfortable with generalities and uncertainties. Geologists often deal with uncertainties on a day-to-day basis. So we have to also use that to manage expectations from folks that may not know about the uncertainties as well as we do. And that would be these tools are not a where's the next rock going to fall from tool. It's not going to say this site here is where the road's going to be closed next. And also to advocate for information to drive the decision making in the where to spend millions of dollars in the rockfall, in this case from rockfall concerns. So that is my presentation. I thank everyone for their time, and boy, I apologize, but there's 1 minute left in the hour.
Thanks, Darren, for your presentation. I appreciate you taking your time and expertise and sharing that with us today. For those of you who are looking for the quiz, we have dropped that in the chat. I'm going to ask Wendy if she could drop that link one more time so that you guys can get logged in to take that quiz. Unfortunately, we're a little tight on time here, so rather than doing the Q&A, I'll leave you with just a couple of quick notes. We will have a PDF of the presentation available to our members behind the member wall. And I would ask Darren, maybe if folks are not members, if they wanted to get a copy of that PDF, or if they had questions, would they be able to just reach out to you directly?
Yes.
Yeah. So if you would reach out to Darren. Darren, would you mind maybe dropping your email address in the chat quickly so that folks can have that?
You betcha. We'll do that right now.
Fantastic.
It's pretty tough to narrow such a large subject matter down quite a bit.
Oh, absolutely. And I do think today's talk was fantastic. So I will encourage you, if you have questions, to reach out to Darren. I'll also let you know that next month we'll have Tom Herbert doing a follow-up on natural hazards in Florida. So we'll go from steep mountain slopes to karst caves and sinkholes. next week or next month. I really appreciate that. And thank you all for coming. If you have any questions, feel free to reach out. And if you're interested in giving a AIPG Lunch and Earn webinar, please reach out to me directly. My email address can be found on the AIPG website. Thank you so much.